All right. So we were talking about dehydration last time. And the mechanism depends on whether we have a primary, a secondary, or tertiary alcohol. If we have a primary alcohol, we get an E2 mechanism. If we have a secondary or a tertiary, we get an E1 mechanism. All right, so that's where we left off last time. Rate of reaction corresponds to the ease at which the carbocation is formed. Okay. Rate of reaction corresponds to the ease at which the carbocation is formed. So does that make sense that tertiary is going to be the fastest, right? Okay, so here's typical conditions. I do not want you to memorize these conditions. I'm trying to just give you a comparison here. So tertiary alcohol, heat to 50. Whoops, we didn't do our. Okay, let's try that again. We're just not going to get a break here, are we? All right. So tertiary alcohol, heat to 50. 50 degrees centigrade in 5% sulfuric acid. Typical conditions, okay? Secondary alcohol doesn't form a carbocation as readily. It's going to be more stronger conditions. Heat to 100 degrees in 75% H2SO4. So that would be 75% H2SO4, 25% water. Primary alcohol, heat to 170 in 95% H2SO4. So are you seeing here a trend here? The more substituted the alcohol, the faster the reaction. Why would a primary alcohol, we're not actually making a primary carbocation, so why would a primary alcohol be so slow? Anybody? What do you think? Remember, it's E2. What does an E2 require? Strong base, right? E2, both the base and the alkyl halide or the substrate are both part of the rate-determining step. So we need a strong base. Do we have a strong base here? The base we use to remove the beta hydrogen is conjugate base of sulfuric acid. So that's the we would call this forcing conditions. Goes by E2. Because primary carbocations are too unstable. All right, so, and then let's just label this, because when you come back and look at this page, you're going to think, oh, do I have to memorize that? Typical reaction conditions, don't memorize. And so we already answered the question, why does a primary alcohol need forcing conditions? And that's because the E2 reaction requires a strong base. HSO4 minus is a very weak base. All right, so your book is going to have some examples of elimination of a primary alkyl halide. I don't want you to do it. So I'm going to say don't do dehydration.
of a primary alcohol. Alternative at the end of this chapter. What is the last page of this chapter in your handbook here? What's the last page? Alternative on page what? Very last page. What is it? 47. On page 47. Okay? And what's going to happen is I teach the honors and majors lab. We've already done an elimination. You guys are going to do the same experiment in week 5, and what you're going to find is that you don't get a good result from the primary alcohol. So all of this will make more sense when you do that experiment. I don't want you doing dehydration of a primary alcohol on any of my tests. I know that the sapling, I know that Smith has questions using it. I don't want you to use it. And you'll see more why that is when we get to chapter 5. All right, stereochemical outcome of this E1 dehydration is the same as the stereochemical outcome of an E1 elimination of an alkyl halide. The Zaitsev product. Which can be a mixture of cis and trans. Mixture of cis and trans with more of the isomer with the bulkier groups on opposite sides. More of the isomer with bulky groups on opposite sides. All right, so just as we would expect. And now we're going to introduce something new here about carbocations that we didn't tell you before. This is something that was actually happening behind the scenes in chapter 7 and chapter 8, and we didn't mention it to you because we didn't feel like you were ready for it. Okay, so it's kind of like, you know, when you have little kids, you don't tell them that you tell them that there's a Santa Claus, and then when they get a little older, then they realize that there's no Santa Claus. So now you're ready to know that carbocations are not as well behaved as we have been painting that picture of them being well behaved. One of the things that they do is they do rearrangements. So that means when you go back and you work problems in chapter 7 and 8, there's actually extra products that weren't accounted for that actually do form in those reactions. And really, any time we form a carbocation, we can get rearrangements. So first of all, I want to talk to you about what a rearrangement is, and then we'll talk about when we'll see rearrangements. So it's not every single time, but it's a lot of the time. Some dehydration E1 and SN1 reactions. So we're kind of going this back to chapter 7 and 8. Give unexpected products in which the nucleophile appears to have added to the wrong carbon or the carbon skeletons have been rearranged. And that's actually exactly what is happening here. All right, so here's a good example here. This is dehydration. How do we know it's dehydration? We have H2SO4 and concentrated H2SO4. And this is our expected product. So if I had given you a little quiz before class, this is the product that you would have written. And this is the rearranged, the unexpected product. And it turns out, in this case, the rearranged product is actually the major product. So first of all, we need to know how that's forming, and then we need to know when to expect that and when to not expect that. All right, so we're going to look at the secondary carbocation formed in this example. So in the first step, we protonate the alcohol. I'm just going to go directly to the second step. Okay, actually, let's just show the first step over here, just for fun. I will use the abbreviated form of sulfuric acid. And I'm just going to protonate this alcohol. So I'm going to go over here, grab that hydrogen, break the hydrogen-oxygen bond, and go down here. So this is the second step. In the second step, since this is a primary alcohol that we've started with, we're going to form, it's a secondary alcohol, we're going to form a secondary carbocation. So that's what happens in that step. Let's draw that secondary carbocation. And this particular carbocation is ideally situated to do a rearrangement. So what does the rearrangement look like? I'm going to change colors here so you can see it a little bit better here. What's going to happen is that this methyl is going to migrate over. So the arrow should come from the middle of that bond there, that carbon-carbon bond. That's going to migrate with its pair of electrons. So it's taking its electrons with it. And when it does that, since it's taking both electrons with it, it's now, the carbon that it just left is now a carbocation. It's electron deficient. And that's because it took both of its electrons with it. So now the carbon on the right is no longer a carbocation. The carbon on the left is a carbocation. And you can see that what we've ended up doing here is we've gone from a secondary carbocation to a tertiary carbocation. And we know tertiary carbocations are more stable. So where we're going to see a lot of rearrangement is when we're making secondary carbocations. And if the secondary carbocation can rearrange to a tertiary, it's going to happen. There's nothing you can do to stop it. Okay, so so it turns out that the elimination, which is the second step here, the loss of the beta hydrogen, can occur from both of these carbocations. So I'm going to draw both of them. I'm going to draw the first one unchanged before the rearrangement. And this is the product that is the expected product. And so we're going to have conjugate base of sulfuric acid come in and deprotonate, remove that beta hydrogen, and then form a new alkene. Okay, so that can happen. And that actually leads to the expected product. So expected product. But as we said, we can also eliminate from this carbocation. So this is our rearranged carbocation. And what we're going to expect for our major product is going to be the most substituted alkene. So here's our alpha carbon here. This one's beta, this one's beta, this one is beta right here. Which one are we going to eliminate to make the more substituted product? Anybody? If we eliminate the hydrogen on the more substituted carbon, we'll get a more substituted alkene. So that's the one we're going to eliminate. Okay, so let's go ahead and do that right here. Going to have this come around, boom, grab that beta hydrogen. Going to go down here and make a new carbon-carbon double bond. That leads to the rearranged product. All right, questions on the rearrangement? Anybody? Yes? Yes. Okay, so her question is, we have two different beta hydrogens here. It's going to depend on what I ask for on the test. If I ask for all the products, then I would want you to eliminate the other type of beta hydrogen. Okay, so if I ask for the major product, then I'm going to look for the one that's more substituted. So that answers that. Okay, so the methyl migrates with its pair of bonding electrons from the carbon adjacent to the electron deficient carbon, the carbon from which the group departs, as a result becomes electron deficient. Because that methyl is grabbing that extra hydrogen that actually belonged to that carbon and taking it with them. This is called a 1,2 methyl shift. Rearrangements of carbocations are a general phenomenon and occur when migration of a hydrogen, methyl, or other alkyl group. So it's not just a methyl, it's a hydrogen, methyl, or other alkyl group leads to a more stable carbocation. Let me show you some examples of each. 1,2 hydrogen migration. So it would be something like this. Notice what's different here. We have a methyl, and a hydrogen. Okay, so in this case, we'd have a hydrogen migrate. So there's the new hydrogen right here, carbocation. All right, so that would be a 1,2 hydrogen migration, or you'll also call it a 1,2 hydrogen shift. That's the other thing. And it moves from the neighboring carbon right onto the carbocation. Here's alkyl migration. This is one like we just saw. So this is identical to the one we just saw. So we see that one of those methyl groups is going to end up on this carbon here. It's moved over. And notice we've gone from a secondary to a tertiary. You can also have groups bigger than a methyl. You can have an ethyl migrate. In this case, you can actually have the methyl migrating like this. So that goes here. And there again, we're going from a secondary carbocation to a tertiary. Or we can actually have a carbon from the ring migrate. This is a little trickier to see. We'll do one of these in discussion to give you a little practice here. These are the hardest ones to predict. Let's do this one more time. We're going to redraw this carbocation. And so what this is going to look like is this is actually good. This whole ring is going to migrate. We get a ring expansion. That's a little mind-blowing. It is, but that's exactly what it looks like. And we know that a 6-membered ring is more stable than a 5-membered ring. So not only are we going from a secondary carbocation that has an adjacent 5-membered ring, we're going to a 6-membered ring. Tertiary carbocation. So that's really going to be favored. So let's label all of these guys. So this is a secondary carbocation. It goes to a tertiary. This is a secondary carbocation. This goes to a tertiary. Secondary carbocation goes to a tertiary. Secondary carbocation goes to tertiary. And that's where we're going to commonly see this. Now, I often get the question, can a secondary carbocation go to another secondary carbocation that's about equal stability? In real life, yes, but this is not real life here. In my class, it's going to go to a more stable carbocation, either a tertiary or maybe something that's conjugated, something like that. So that's what you'll see in my class. So what you won't see is a secondary carbocation going to a secondary carbocation that's equal stability, even though that really does happen. Carbocations are not very well behaved. Question?
So which one is more favored, the second?
The second one is going to give you a tetrasubstituted alkene. So the most stable product is going to come from this carbocation. Okay, yeah?
Do all migrations move to a carbon directly adjacent to?
Yes. We're not going to see them moving 2 carbons over, just 1 carbon over. Okay. So in the first example, so the other question that I get is, in this first example, why did we migrate a hydrogen? How do we know we don't migrate a carbon? So let me show you what I'm talking about. So we migrated a hydrogen. How are we supposed to know that a methyl doesn't migrate? Well, let's answer that. I'm going to show that. That's at the very end of this page. Let's try it. Let's try having a methyl migrate instead. We're going to go here. All right, so why doesn't that happen? Yeah, you're just going from a secondary to a secondary. Okay, so in this happy little bubble of the first year of organic chemistry, when everything that works is supposed to work and all of that, and this is not going to happen because we're going from a secondary to a secondary. Okay, in real life, that can happen. Not something we're going to worry about for this class. All right. All right, so whenever a reaction leads to the formation of a carbocation, and that includes reactions, that includes SN1 reactions, E1 reactions from chapter 7 and 8, you must check its structure for the possibility of rearrangement. Will I tell you, hey, this is going to rearrange? No. You're going to know that you form a secondary carbocation, and whenever you form a secondary carbocation, you need to look for rearrangements. So you need to know how to do that on your own. I'm not going to warn you. Okay, so this guy, these are the expected. The ones that are from rearranged carbocations, I'm going to put an asterisk next to them. So this one here, that one here. Which product is major? What do you think? The fourth product? Yeah. Tetrasubstituted alkene. And here's a dehydration example. This is just like the one that we just did. And so definitely this is the rearranged product. So that's what the asterisk means, from rearranged product. And so definitely this one's going to be the major, the second one drawn, because it's a tetrasubstituted alkene. All right, so let's summarize dehydration reactions. Use H2SO4 concentrated, or TSOH, toxic acid, plus heat. We want heat, so it favors elimination. Works for secondary or primary alcohols. Don't use for primary alcohols. Use alternatives shown on page, that was what, 46 or 47? What was it, 47? So change that to a 47. Watch for rearrangements, especially with secondary alcohols, and most highly substituted alkene is favored. Okay? All right, so that's dehydration. Now we're going to move on to the second part of this chapter, which is all about taking alcohols. And alcohol has a really poor leaving group, doesn't it? Taking an alcohol and converting it into something that has a good leaving group. That's the major bulk of this middle part of this chapter. And so an alcohol cannot undergo a nucleophilic substitution because it has a strongly basic leaving group that cannot be displaced by a nucleophile. So if you're thinking that this can happen, you may want to take another look at chapter 7. And what we said in chapter 7 is we're not going to have hydroxide as a leaving group in an SN2 reaction. So if you're thinking this is going to happen, that's not going to happen. Let's put a big X through that. That's not going to happen. But what we're going to do is we're going to figure out some ways that we can make a similar thing happen. Not by this method, but by something that's a little bit different. And this is all because this is a bad leaving group. It's a strong base. We know that good leaving groups are weak bases. Strong base, pKa of the conjugate acid. Conjugate acid of hydroxide is water. Is approximately 15. So that's sort of in our category of bad leaving groups. All right, so if an alcohol can undergo substitution, if the OH group is converted into a group that's a better leaving group. So how about a halogen? If we can take that hydroxyl, we can't do it this previous way that we have on this page, but if we take that hydroxyl and we move it, we convert it into a halide, then we can do all the reactions from chapter 7 and 8, right? So, and there's a way to do that. We can take the alcohol and treat it with HX. Converts the bad leaving group hydroxyl into a great leaving group. So this is what it looks like. Bad leaving group. And let's repeat what we had on the previous page. pKa of the conjugate acid, H2O, is about 15. And if we treat this with HBr, we can actually convert this into methyl bromide. And side product is water. All right, so now we've taken that bad leaving group and converted it into a great leaving group. pKa, how do we know it's a great leaving group? pKa of the conjugate acid, HBr, is -8. It's a fantastic leaving group. So that's what we want to do. Take the alcohol and convert it into an alkyl halide. So that's the first reaction we're going to talk about in this section. It turns out that we could do this with primary, secondary, and tertiary alcohols. All undergo nucleophilic substitution when treated with HI, HBr, and HCl to form alkyl halides. No HF. This HF does not work in this reaction. So primary, secondary, and tertiary alcohols can be converted into Rx, where X equals I, Br, and Cl. So that's what we're doing in this part of the chapter. Mechanism is going to depend on the alcohol used. So primary alcohols and methanol, reaction proceeds through an SN2 type mechanism. Secondary alcohols and tertiary, those are going to proceed by an SN1 type mechanism. So it's kind of similar to dehydration. We have a different mechanism depending on the alcohol we start with. So let's do primary alcohols and methanol first. First step. So this is a potential mechanism for midterm 1, right? What are the potential mechanisms for midterm 1? We have elimination, we have E1, we have E2. We also have dehydration, dehydration with a primary alcohol and dehydration with a secondary or tertiary. So we're already getting quite a list of possible mechanisms. This is another possible mechanism for midterm 1. And you're pretty much guaranteed to have more than one mechanism on this first midterm. I emphasize mechanisms quite a bit because they help you learn organic chemistry. They help minimize your memorization, okay? So it's really helpful. All right. Looks like the first step of dehydration, doesn't it? All right, and what we've done there is, in a kind of roundabout way, we've taken our bad leaving group, and a good leaving group in our intermediate, okay? Now, in the step 2 of this reaction, I'll just redraw this. Our good nucleophile, bromide ion, is a very good nucleophile. It's going to come in and do an SN2 reaction. So bromide's here. So that's our conjugate base is going to come in and it's going to do backside attack, kick off our leaving group. And you can see where our side product is coming from. That's when water leaves. So we've gone from a bad leaving group, and our ultimate product here is this, which has a great leaving group. Questions on a mechanism for primary alcohol and HBr? Anybody? Let's look at secondary. Reaction proceeds through an SN1 type mechanism. Here's an example here. Tertiary alcohol, HI, converts it into terp-butyl iodide. All right, so the step 1 is going to be exactly the same. We're going to protonate the alcohol, so let's do that here. All right, so I'm pretty particular on my mechanisms. I want to see lone pairs on all reacting atoms. If you're breaking a bond, I want you to draw it. Draw any bonds that are breaking. Arrows need to come from a lone pair or a bond. So here this arrow is coming from a lone pair. The second arrow is coming from a bond. So it will look like that. This is a very fast reaction. Acid-base reactions are extremely fast. So that's a fast reaction. All right, so we protonated the alcohol. Now, if you're thinking that iodide can come in and do backside attack, that's not going to happen. Why is that? It's a tertiary alcohol. It's a tertiary. So that's not going to happen. All right, so we're going to lose water to form a carbocation. So far this is looking just like dehydration, huh? So we have a protonated alcohol. Tertiary carbocation. Same thing will happen with secondary. We'll get a secondary carbocation. And if we get a secondary carbocation, what do we watch out for? Yep, if you can have it. You can't always have it, but so this is a fast or a slow step? Slow step when we form a carbocation. And then we have nucleophilic attack at the carbocation. So I'm going to redraw this. Okay, so the arrow is going to come from one of the lone pairs on iodine. Iodine is involved in the arrow pushing for this step, so it needs all of its lone pairs. So it's going to come and attack the carbocation. This is also a fast reaction. So that's the mechanism that we're going to see when we have a secondary or tertiary alcohol. All right, important points, order of reactivity. For HX, HI is fastest, followed by HBr, followed by HCl. And why is HCl slower? Well, it really comes right down to this step right here. Chloride ion is a weaker nucleophile. Okay, so that's slower. Slower because Cl minus is a weaker nucleophile. And it's so weak, in fact, that in your book, in your textbook, the book uses zinc chloride to promote the reaction. To promote the reaction. In other words, HCl on its own isn't good enough, so they take HCl and react it with zinc chloride. I'm not going to have you worry about the zinc chloride. I think we're just going to pretty much stick to HI and HBr, and then we can avoid the whole zinc chloride issue altogether. Okay, so that's how I usually handle it. Questions on that point? Anybody? All right, so order of reactivity for alcohols. Tertiary is faster than secondary, is faster than primary, is faster than methyl. Okay, so these guys, these undergo SN2. These guys undergo SN1. So what that's saying is that a secondary alcohol, it's faster to make a carbocation than it is to undergo backside attack. It is much faster for a secondary carbocation, for a secondary alcohol to make a carbocation. Maybe a little surprising, but that's really what that is telling us. So it's faster for a secondary alcohol to form a carbocation than to undergo backside attack. So SN2. Maybe surprising, but that's actually the case. It's actually faster. And that's because SN2 on a secondary alkyl halide, that's beginning to get very sterically hindered, and that slows the reaction down tremendously. So this reaction is best for primary, methyl, and tertiary substrates. Reaction doesn't work well for secondary. And I don't want you to use it for secondary. I'm going to show you some alternatives coming up. Okay, so don't use for secondary substrates. If we have a secondary alcohol, we want to turn it into an alkyl halide, we're going to use another reagent. Don't use for secondary substrates. Why is this? Why? Why not secondary substrates? All right, so here's the reason, the long reason. Secondary substrates can undergo both SN1E1 and SN2E2 depending on the conditions used. Under the conditions of this reaction, strong acid, strong aqueous acid, SN1, E1 pathways are favored over SN2, E2 pathways for secondary substrates. It is faster to make a carbocation than it is to undergo backside attacks. So the reaction proceeds by way of a carbocation intermediate which can rearrange. So now that we're alerted to rearrangements, that's what's we're going to have to worry about those happening. So let's go through this example here. Okay. Let's draw the product of that step. We have now a protonated alcohol. This is a secondary alcohol. We have a protonated alcohol, so the next step is going to be for the leaving group to leave. So let's draw the protonated alcohol. And then this is going to leave. All right, let's draw that carbocation. We've already seen that a couple of times, and you'll see it in discussion also this week. Okay, so secondary carbocation, bells should be going off in your head saying, okay, look for rearrangements, look for rearrangements. And we have a nice rearrangement here. We can do a 1,2 hydride shift. So let me change colors for that. Just like this. So the arrow should come from that carbon-hydrogen bond to move over to the carbon. So there's a tertiary carbocation. So either one of those products we can get products from both of those. Let's draw both of them. If the bromide attacks before that rearrangement happens, we can get this product. Or if we do rearrange first before the bromide attacks, I'm skipping a step here, then we can get this product. So that reaction that we were trying to do actually yields two products. So if we wanted to get the unrearranged product, then we would have to separate those two compounds, which is not trivial to do. Those are pretty similar physical properties. It's going to be tricky to do. All right, so we want to use an alternative. Yes, question?
Does the hydrogen, when it's rearranged, does it sit on either or is it kind of stay on both?
Before it rearranges?
No, once a carbocation forms.
Yes.
If you're looking at the molecular orbitals, is the hydrogen sitting on both, or is it just sitting on
Not really. We'll talk. You can come up and we'll talk about that after class. Okay. That's reason number one, rearrangements, right? Reason number two, let's talk about the stereochemistry of this reaction. You love stereochemistry, right? We don't want to leave stereochemistry out. Depends on the substrate used. Primary alcohols. I might give you a problem like this on the test, and I'm going to expect you to show the stereochemistry in the product. So let's say we started off with this optically pure. Primary alcohol. How do we have an optimally pure primary alcohol? We use deuterium for one of the hydrogens to distinguish those two hydrogens from each other. Let's go through the mechanism. If you know the mechanism, you will have no trouble predicting the product. If you don't know the mechanism, it's a 50-50 guess. So we'll see how lucky you are on the test if you just do a 50-50 guess. All right, let's go through it. We know the mechanism, so this should be easy to predict. That hydrogen's going back, this deuterium is coming forward. All right, what happens next? Elimination, right? No? Substitution, right. See, I tricked you there. All right, backside attack. SN2, inversion of configuration. SN2, inversion of configuration. So you want to show inversion of configuration, so I'm going to have the bromide coming in from the opposite side. There's more than one way to show inversion of configuration. If you have another way to do it, that's also fine. If you have the nucleophile coming in from the opposite side, then we just move the hydrogen over to this side, and we move the deuterium, but we keep them in the same orientation. And that will give you, so that's SN2, inversion of configuration. It's 100% inversion of configuration. So 100% inversion. Need to know that. So in the product, you will draw inversion. What happens at the secondary or a tertiary alcohol? Let's go through that. If we know the mechanism, that's not a hard question. If we know the mechanism and we know the structure of a carbocation, that is not a hard question. It's really not a 50-50 guess, because you could have one enantiomer, you could have the other, or you could have both, right? So that's a 1/3 here. 1/3, if it's a guess, you got 1/3 of a chance to get it right. All right. So let's go through this real quick here. We know a little bit about the structure of a carbocation. So this is a secondary alcohol under these conditions. The alcohol leaves, we form a carbocation, and we do SN1. Structure of a carbocation, well, gosh, the carbon of the carbocation and all the 3 atoms attached are all in the same plane. Hydrogen goes back. Here we have a methyl. All right, so these guys are all in the same plane. Not every single atom there, but all of these groups, this carbon, which is the carbocation, this carbon, that hydrogen, and this carbon are all in the same plane. So now think about the next step in this reaction and what kind of stereochemistry you'll get. We'll talk more about this on Friday.